Ooh, can we get some color on those slides? Yuck.
No.
Hi.
This
That's
is
how
the
he
vibe.
likes it. That's how Ryan does his slides. Not
Quiet in the
others.
front.
Okay, so thank you everyone for being here today. I'm very, very proud to have my my PhD student Ryan give his defense presentation. So the way it's gonna work is that, Ryan, are you okay with questions in the middle, or you want them at the end?
Yeah, sure. Ask questions whenever.
Feel free to ask questions, raise your hands. So Ryan's gonna finish his presentation, then we're gonna have a few minutes available to ask more questions. Then I'm gonna ask anyone who's not in the committee to go outside and wait while the committee asks more questions to Ryan, and then Ryan is gonna go outside and the committee will make the final decision. Hopefully it's gonna be a positive and then we get to drink the champagne, okay?
Yes.
Or
the whiskey, in case it goes the other way. Actually, Mike, could you give Olga that form there? Okay, so I'm Ryan. Today I'm going to be talking about turning machine learning inwards and different techniques we've developed for automating some of the complexities of cloud databases. So my committee, Olga, Magda, and Luba, heard the kind of technical in-depth version of this presentation when I defended my proposal. So today we're going to try to take a more visual and intuitive look at the problems. We're going to look at a lot of different demos of the techniques that we developed to try to better understand them and get a high-level understanding instead of diving into the nitty-gritty. In case you get bored or you only want to pay attention for 1 minute, here's the entire thesis in one slide. The dominant pattern in the last 10 years has been that the cloud is providing a very cheap alternative to data centers. However, because the cloud is providing a very cheap alternative to data centers, a lot of businesses that were previously not involved in data management technologies are becoming more and more involved. So whereas before only the really big players could afford to have a large data center and hire DBAs, the cloud is allowing a lot more businesses to access those resources. Because of this, there's a very high application diversity and a very wide range of needs that are accessing cloud computing environments. Unfortunately, the complexity of using these cloud computing environments is significantly larger than the complexity of managing a traditional data center. So our argument is because of this significant increase in complexity and because of the significant increase in application diversity, we should replace the traditional ad hoc heuristics that we use in traditional data center-based approaches with applications of machine learning. So to give an outline of what I'm going to talk about, first I'm going to explain what exactly makes the cloud complex and makes it harder to deal with in a data center. And then we're going to talk about 4 different systems that we've developed here at Brandeis over the course of my time here and how they solve some of these problems. So starting out with the complexity of the cloud, in a traditional data center you have a fixed number of nodes. You kind of look at your workload and you figure out, okay, we need 100 computers, so you send a PO and you go and you buy 100 computers. The hardware configurations of those computers don't really change. Maybe you upgrade their storage, maybe you get a little more RAM, but more or less the hardware that you buy is the hardware that you get forever. Because you have to buy all the hardware you're ever going to need, you have to provision for what's called maximum capacity. So if some point during the day you need 100 computers to handle the peak load at 5 p.m., then you have to buy 100 computers, even if most of the time you only need 20 or 30 computers. So because you have to provision for your maximum capacity, you have to pay for your maximum capacity 24/7. You have to pay to maintain, keep on, pay the electricity bill and the cooling bill for all 100 of those machines, regardless of how many you're using. However, data centers do provide a lot of benefits. One is they give you very consistent performance. When 5 p.m. rolls around, other Amazon customers or other Google customers aren't using your CPU cycles. And the landscape doesn't change underneath you. If Amazon decides to upgrade or downgrade their machines, that affects you as their customer, but in a traditional data center, you own your computers. It's also a very familiar API. We've been dealing with the Distributed Data Center API for decades, and we have lots of good algorithms and lots of powerful abstractions to help make them simpler. Clouds bring a lot of complexity to this scenario. Instead of provisioning for your maximum capacity, instead you get this idea of elasticity. So when your load is very, very small, you can use just a few computers, and when your load is very, very large, you can provision more computers. Additionally, the hardware configurations aren't fixed. So at some point you might be able to get a computer with a lot of RAM, or you might be able to get a computer that has a much faster CPU, or you might even be able to get a computer with special networking hardware or specialized hardware like GPUs or FPGAs. So because you provision for your current capacity, This means that you can pay as you go. You don't have to be paying for your maximum capacity all the time. That's quite nice. You only have to pay for 20 computers when you're using 20 computers, and you don't always have to pay for 100 computers. However, they come with a lot of downfalls as well. First is shifting performance. The cloud landscape is changing all the time on a daily basis when there are spikes in workloads, and on a monthly basis as cloud providers compete with each other and provide different options. They also have a much more challenging and complex API. Now you have to deal with network boundaries, you have to deal with multi-region stuff, and you have to deal with making your systems elastic, being able to add and remove a cluster to a node at will. So all of these things add a whole lot of complexity. Just to put some numbers on this, if you were to look at the Amazon EC2, which is their dynamic infrastructure page, in 2016, you would have seen 32 different offerings. A year later, you would have seen 45. About a year ago this time, there were 61, and last week when I checked, there were 173, and that's a real number. There are 173 different machine types that you can rent from Amazon right now. And that's just the complexity on the Amazon cloud. There are also new, although they're not really that new anymore, players like the Google Cloud Platform, Azure, Linode, IBM, etc. So the landscape is immensely complex and getting more complex every day.
Can you say anything about the difference in security between these two types?
Yes, they're all bad. Oh, you mean between data centers and clouds? Or between different clouds?
Yeah, between data
yes.
centers and clouds.
So the security concerns in the cloud are, there are some advantages and there are some disadvantages. If you're a small firm that doesn't really have good IT practices, if you can't hire a security person or if you can't hire someone else, it's possible that whatever Amazon is doing by default is better than what you would do to secure that machine. If you're a big corporation like Farmers Insurance or Geico or something, then you probably have security people, and those security people are probably much, much better than whatever Amazon is doing to secure your cloud. So in terms of security concerns, it kind of depends on who you are, but in general, if you have the money and you can hire the experts, the data center is going to be better. So all of these complexities lead us to an unavoidable conclusion that architecting systems for these cloud environments is very, very, very hard. Specifically, the minimum set of challenges that you have to deal with if you're thinking about a database application is cluster sizing, deciding how many nodes that you want to be inside of your cluster, query placement, deciding which types of queries should go on what type of nodes. I need to put my CPU-bound queries on nodes with fast CPUs. I need to put my storage-bound queries on nodes with fast storage, and scheduling. Once I've decided where to put these queries, what order do I execute them in? Which queries have a higher priority to the user? How do I organize that? Unlike in a traditional data center, all of these components have very complex interactions with each other. Your scheduling algorithm needs to know about the cluster sizing. If your scheduling algorithm is coming up against a deadline very, very frequently, you might need to make your cluster bigger in order to handle that. So all of these complex interactions between these components exist in the cloud environment, but don't really exist in the data center environment. When we're architecting systems for the cloud, we want to have two distinct goals in mind. The first is that we want to be agnostic to the application specs. Because the cloud is allowing more and more people to use data management technology, we need to be able to handle the arbitrary workloads that come with that. So we don't want to be thinking about just a bank's workload or just Amazon's workload. We want to kind of say, what's the most generic sort of framework that we can create that will allow almost anyone to use these systems? The second thing we need to think about is application-defined performance goals. If you're Amazon, you probably care about a search query or a purchase query going through in a fixed number of milliseconds. You don't want the user to have to wait more than 200 milliseconds or 500 milliseconds or something like that. But if you're a data analysis firm, you probably care much more about the total throughput of your system. You don't care if one query takes 3 seconds. You just want to be able to process your entire report before your monthly deadline. So because of this, different organizations have different performance needs, and we need to build systems that can adapt to those arbitrary goals. So we're not going to be able to handcraft a static heuristic for each one of these different situations. Previously, when you were in a data center and you were a big corporation, you'd hire an army of DBAs and hire an army of programmers, and they would arrange your database for you and make everything work well. That is no longer possible for the new clients that are coming into the cloud. So because these handcrafted static heuristics aren't going to scale to the cloud, we argue that we should instead use machine learning techniques to try to augment or automate as much of this process as possible. So next we're going to talk about the various systems that we've developed in an attempt to do that, and we've kind of created a hierarchy of them. So we've created 4 types of systems. We've created planning systems. These are systems that allow you to explore your options and assess cost versus performance trade-offs. And we've created predictive systems, which try to minimize costs directly in an online fashion or try to make some kind of prediction about the future. We've additionally divided these projects into top-down and bottom-up systems. Top-down systems take a holistic view of the cloud, and they don't really focus on database internals. They look at how do we size the cluster and things like that. And the bottom-up systems get into the nitty-gritty of the database. So we're going to go through these in order. The first system that I want to talk about is WiseDB. WiseDB is our system for exploring cost versus performance trade-offs in cloud databases. So the system model that WiseDB assumes is that you have a user, they have some queries, they're going to submit those queries to a cloud data management application, and that cloud data management application is realized by running some kind of relational database like Oracle or MySQL or Vertica on top of a number of virtual machines in sort of a fully replicated environment. And in this environment, we have two primary goals. The first is that we want to meet the performance goals of the user, and the second is that we want to reduce costs. So what WiseDB does is tackle these challenges. And to give you sort of an example of what that might look like, imagine the user submits the 4 queries here. The first thing the user needs to decide is how many virtual machines am I going to use to process these queries and what type. So maybe you think, okay, well I need these 2 types of virtual machines, so I'm going to provision those, I'm going to ask for them for the cloud, I'm going to wait 20 seconds, and now I've got my machines. Then you need to decide, okay, which one of these queries is going to go on which one of these nodes. And to do that, you might look at some kind of affinity metric, like, okay, well, these are compute bound and these are storage bound, so these are going here and these are going here. So you make that decision and you decide, okay, these 2 queries go on this machine and these 2 queries go on this machine. After you do that, you then have to make scheduling decisions. You have to decide what order am I going to execute these queries to best meet the user's application goals. So for example, you might decide that the correct order to place them in is something like this. So with deadlines, when you have a deadline-based constraint, this problem becomes the bin packing problem, which is NP-hard. So because it's NP-hard, we're not going to find, we're probably, unless P equals NP, assuming P does not equal NP, we're not going to find a nice polynomial time solution that solves this in every case. So what we do instead is we're trying to come up with heuristics. Traditionally, people have come up with heuristics like first fit decreasing, or like always sort your queries like this and then do this weird thing. What we're going to try to do instead is learn those heuristics. So what we want to help users do is generate end-to-end strategies to help them schedule, provision, and place queries in batch workloads. And we want to specifically focus on how we can design tools that can help users explore cost versus performance trade-offs. So WiseDB assumes that it gets 2 particular inputs. The first input it gets is a set of query templates, and you can sort of think about these as latency bins. So the user might say, okay, well I have some queries that take 2 minutes and I have some queries that take 1 minute. Then the user provides an SLO, or a service level objective. This is their performance goal. So they might say, I want my blue queries to finish within 3 minutes, and I want my green queries to finish within 1 minute. We call this entire thing a workload specification. It specifies sort of what the user is going to be sending us and how the user wants that to perform. And so we send this workload specification to WiseDB, and offline WiseDB does some computation and eventually says, okay, I'm ready. Here's what you get. So WiseDB from this produces 2 outputs. The first thing it produces is a scheduling strategy. And the scheduling strategy says, okay, user, if you give me 3 blue queries and 2 green queries, I'm going to feed those into a scheduling strategy, and then out will pop a full cloud resource deployment. So I will tell you how many virtual machines you should have, where you should put each query, and what queries and what order you should execute those queries in. The second thing it will output is other recommended service level objectives and their costs. So for example, the user might have said, okay, here are my 3 blue queries, my 2 green queries. They gave us an original deadline, but WiseDB will suggest, hey, if you increase your deadline to 4 minutes, you can do this for just $2. Or if you increase your deadline to 5 minutes, I can cut your cost in half to only $1. So the way that WiseDB does this is is through a very specific graph-driven technique. So we know we can't find the optimal solution for very large NP-hard problems. If we just took 1,000 queries in an arbitrary deadline, we could never brute force the right answer. However, what we can do is we can find the optimal solution to many instances of very small NP-hard problems. So if we only have 3 or 4 queries, it's very easy for us to find the optimal layout. We can just brute force it. So what WiseDB does is it creates many, many, many small examples of these small workloads, brute forces the solutions to those, and then tries to learn the patterns in the solutions to the small examples to apply them to the large examples. So instead of climbing one giant mountain, we're going to climb a lot of tiny hills. So I'm not going to go into the technical details of how this works, but I'll give you a high-level overview. So the first thing we do is called workload sampling. We look at the user's latency bins that they gave us, and we construct a whole bunch, like approximately 1,000 or 2,000, very small workloads, small enough so that we can brute force them. Then we represent the problem of assigning all of these queries to their clusters as a graph. After we've represented it as a graph, we use the A-star search algorithm to find the optimal path through that graph. And the optimal path through that graph represents the optimal answer to our bin packing problem. And so we can extract all the vertices along that optimal path, and each vertice represents a decision that the algorithm made, and we can use each one of those vertices as a training set. So the problem then becomes, if I'm at this vertice in my problem graph, which edge do I want to follow? And so we can treat that as a classification problem, and so we simply train a decision tree classifier on top of those vertices. And these decision trees look something like this. So the details aren't super important, but basically what this decision tree says is, if the last virtual machine I created has a wait time of less than 3 minutes, and if I have a green query, then I should place my green query onto a virtual machine. If I don't have a green query and I have a blue query, then I should place the blue query onto the virtual machine. So this tree encodes the strategy that I've written in kind of pseudocode on the right. While my wait time is less than 3, place a green query if I have one, continue. Place a blue query if I have one, continue. And finally make a new virtual machine. So when we apply this tree to this set of queries, 3 blue and 2 green, we get this deployment strategy. We place the 2 green queries, then we place the blue query, then we create a new virtual machine, then we place the 2 blue queries. So these decision tree models allow us to encode an entire strategy that handles all 3 of the things we want to deal with: provisioning, placement, and scheduling. So the way that WiseDB does its scheduling recommendations is by using this primitive of being able to look at to find the optimal cost for a particular deadline, and it creates a graph that sort of looks like this. So on the x-axis we put the deadline, so the strictest deadline is at 0 and the loosest deadline is at the end of the x-axis, and then we plot the costs that occur at that point. And when we do this, we notice a plateauing behavior, and this plateauing behavior happens whenever another query fits. So for example, if all of my queries take 1 minute and I have a 2-minute deadline, if I extend that 2-minute deadline to 2.5 minutes, that doesn't really change anything. But if I extend it to 3 minutes, suddenly now I can fit 3 queries in serial before I hit that deadline. And so the result of this is this plateauing behavior where suddenly you loosen your deadline by a little bit and you get a big drop in your cost. So what WiseDB does is it finds these plateaus, it finds the strictest deadline that has a particular cost, and we assume that these are the SLAs that are interesting to the user. So I think seeing this is a little easier than thinking about it just conceptually. So here we've created a demo, and so in this first part we specify our latency templates. So here I'm going to specify that our workload consists of 3 different queries, one of them that has a latency of 2, one that has a latency of 3, and one that has a latency of 4. Let's save that. Next we give the second part of our workload specification, which is the deadline, and I'm going to say, all right, I want these done in 9 seconds. I'm going to ask it to do the WiseDB thing. So this is the offline phase where WiseDB has to think for a little bit and come up with some answers for us. Okay, and the resulting output is that we get a strategy. If I have 5 instances of Q1 and 5 of Q2 and 5 of Q3 and my deadline of 9, then the best thing to do is to place 1 instance of Q3 and then a Q2 and then a Q1. By doing this, the sum of the latencies exactly adds up to 9, and I hit my deadline perfectly. When we do the exploration, when we vary that deadline and solve the problem again, we find a couple of plateaus. The first plateau, or the loosest plateau that we find, is at 19 seconds. So if you change your deadline to 19 seconds, your ideal scheduling strategy changes to look something like this. Now you put a whole bunch of Q3s together, and then your Q2s and your Q1s. This causes your cost to go from 11 cents to process with the 9-cent deadline to only 8 cents. Additionally, by changing the deadline to 11 seconds, we can save 1 cent, and if we were to tighten the deadline to 8 seconds, we could do that for only an additional cent. So the point of this tool is to show the user the relationship between the deadline that they request from their cloud environment and the cost that's going to happen. And we think that this tool provides a powerful planning phase for people to figure out, well, okay, what exactly are the cost versus performance trade-offs that are going on here?
Is the time it takes and the cost kind of have a more linear or a very non-linear relation?
So in this example, we assume it's linear. So if the user's query latency bins are like 1 minute and 2 minutes, then we assume that the cost to run something for 4 minutes is double the cost for 2 minutes. So on some cloud providers, this isn't the case, right? So for example, on Azure, you get rounded up to the nearest hour, and that's all you get. But more and more cloud providers are moving towards per second billing, So we think this linearity assumption is mostly true.
And then does your suggestion sequence, does it matter on this? I guess not. It doesn't matter what the cost profile goes with the time.
Yeah, so that definitely matters. So that we encode in the SLO, or the objective. So WiseDB is searching. So for example, if you have a deadline, if you say, I missed this deadline, that cost me $1, then your cost function is now not linear, right? Now it goes straight, and then it has a spike. So WiseDB is searching not just to minimize your cloud cost, but it's to minimize that cost as well. And the way that we encode that is we tell the user, draw us your cost curve, and we'll figure it out.
I have a question. Are you assuming that each query runs in its own VM?
Yes, so right now, WiseDB assumes that each query is run in serial on its own virtual machine. We will relax that requirement in a minute.
To get a new SLA estimate, do you have to retrain the decision tree, or do you take that one decision tree and apply it to the new SLA?
So to tighten an SLA, what we notice is that if you tighten your SLA, then every path that you pick on that scheduling graph, the cost can only go up.
Mm-hmm.
And so because the cost can only go up, the previous graph serves as an admissible heuristic for the new graph. So you can use it as the A-star heuristic. So we can't reuse the same decision tree, but we can reuse the same scheduling graph. So when we tighten the deadline, we reuse that same scheduling graph, and we find a solution much faster. The details of all these things are obviously in the dissertation as well. So I just showed you an example of a particular deadline where we cared about the maximum time, the total time. We also evaluated WiseDB across a number of other performance metrics. So, for example, two very popular heuristics for solving this problem are FFD and FFI, first fit decreasing and first fit increasing.
Could you please stand a step back?
Oh,
have a hard time.
sorry, that good?
Thanks.
Is that gonna work?
That is good.
Okay, cool. Yeah, sorry, there's a lot of angles here. So if you're dealing with a max SLA, then the traditional algorithm that you would use off the shelf is first fit decreasing. You would sort your queries in decreasing order, and then you would place them in the first orders that they fit. However, if you were trying to minimize the average latency, then you would want to put your shortest job first instead of putting your longest job first. And so what we're showing here in this graph, in those max and the average columns, is that WiseDB learns a heuristic that is competitive with the ideal heuristic for that particular deadline. So it's not that WiseDB is going to find some kind of scheduling strategy that's way better than a hand-tuned heuristic possibly could. The point of WiseDB is that no matter what your performance SLO is, no matter what those performance goals is, we're going to find a strategy that's competitive with the heuristic you would have came up with if you sat down and hired an expert and thought about the problem and proved all those nice bounds. So in the paper we show it for an additional type of SLO as well, but I didn't want the slide to get too crowded. So yeah, that's the idea behind WiseDB. So WiseDB, after we worked on WiseDB and we came up with this nice planning situation that let people explore the cost-benefit trade-offs of their SLOs, we started thinking about, okay, well, how can we process online workloads in a way that minimizes cost? So again, we have the same situation where we assume the user is submitting queries to a cloud data management application. There's some kind of relational database that's replicated across a bunch of virtual machines. And again, I want to meet my performance goals and reduce my costs. What's changing is that whereas WiseDB was focused on exploring options and understanding cost versus performance trade-offs, Bandit's not going to do that. What Bandit's going to do is it's going to take your service level objective, whatever goal you've finally chosen, and it's going to try to execute it in the most efficient way possible. Whereas WiseDB assumed your workloads came in batches that we knew ahead of time, Bandit will be a completely online algorithm. In WiseDB, we assumed we knew the latencies of the queries ahead of time, that they fell into various latency bins. In Bandit, we will not make that assumption. So we make a delineation that WiseDB is a planning system. It's a system you use before you start executing your workload to kind of figure out what you want, and that Bandit is a predictive system. It's a system you run online with your queries to try to minimize cost. So the core algorithm inside of Bandit is something called a contextual multi-armed bandit. So imagine that you're on a game show, and in this game show, you get to choose repeatedly between one of three doors. You're going to open the door, and then you're going to receive the prize that is behind that door. And there's no fancy tricks. You don't get to open one door and peek. There's nothing like that. All you get is an opaque vector, 130, 600. You get some piece of information, and from that piece of information, you have to decide which door you want to pick. So initially, you have absolutely no information. You don't know anything at all. So the best you can do is randomly guess. So let's say that we randomly guessed door number 1. We say, I'd like door number 1, please. We open door number 1, and we receive $5. That's great. So we write down, okay, when I got $5 when I opened door number 1, and the context was 130, 60. Then the game resets, and you get a new context vector, this time negative 90, 62, and 8. And we still don't really know a whole lot of information, but I tried door 1, so I might as well do a little bit of exploration. So maybe this time I pick door 3. Maybe I open door 3 and I see $1. Ooh, not nearly as good as the $5 I got before. So I write that down into my experience. I got $1 when I opened door 3 when I saw this particular context vector. And you repeat this process a lot, and over time, eventually, you hope to learn the relationship between the context vector and which door has the highest reward. So maybe, for example, it's the case that door number 1 contains $5 when the first entry of that vector is positive, right? And if we do this process enough, if we open up enough doors and we record enough experiences and we do the learning just right, we can hopefully understand the relationship between the context vectors and the doors. So this is a classic reinforcement learning problem. It's a classic bandit problem. There are lots and lots of nice algorithms to solve for them. I'm not going to talk about those today. Instead, I'm going to assume that we have those as a primitive. So if you want to Google them later, the 2 algorithms that are most commonly used are the least upper bound algorithm, and the one that we actually use is called Thompson sampling. So the idea with Bandit is that each virtual machine in the cluster is going to pretend that it's playing this multi-armed bandit door game. So we're going to arrange our virtual machines into tiers. So tier 1 will contain our cheapest, slowest type of virtual machine. And tier 2 will contain more expensive machines. And tier 3, the most expensive. And you might have more than 3 tiers. When a query arrives, we're going to send it to this virtual machine first, the first one in our first tier. And that virtual machine is going to make one of 3 decisions. It's going to look at the query, it's going to look at its context, what's going on, what does it know about the query, what does it know about its current state, and it's going to decide, okay, should I accept this query and process this query myself? That's door number 1. Door number 2 is write. Should I take this query and send it to my neighbor? Should I say, hey, I don't want to process this query, I don't think it's going to work very well, I'm going to send it to the right to my neighbor? Or should I say, wow, I don't have nearly enough memory or resources for this. I'm not going to be able to do this, and no one on my tier is going to be able to do this. So I'll pick door number 3, which is labeled down. When the down door is chosen, the query is passed from this tier down to the first virtual machine on this tier. Each one of these virtual machines runs this algorithm simultaneously, and they each keep track of their own experience, and they each try to learn how to play this game ideally. So a couple of observations about this game. Because each one of these virtual machines and intelligence agents is sharing a reward signal, so if one virtual machine patches to the right and then the next virtual machine chooses to accept the query, they both get the same reward. So they are cooperating, and so we can think of this as kind of a co-learning or co-evolutionary system. And the other observation we can make is that the tiered network of the way that we've arranged these virtual machines and these bandits gives us a lot of benefits that naturally help us adapt to the cloud. The first is it gives us elasticity. When you press that right button and there's no virtual machine to your right, that's when we know we need to provision a new machine. When you press the down button, that helps us deal with the hardware tiers, right? So on a modern Amazon deployment, maybe you'd have 173 of these tiers, and you'd have your queries pass down between them. More realistically, maybe you'd pick 8, right? So again, seeing is better than looking at slides. So let's see how the system behaves. Yes?
What's the reward signal they're getting in this case?
So the reward signal that they're getting is the cost. So the actual dollars spent on the cloud in order to execute that query. Plus any penalty incurred from missing their deadline. So we're going to change this. We're going to say instead of using WiseDB, we're going to use the Bandit algorithm. This takes a couple seconds. So what you're seeing here on the stage left is initially Bandit is booting up a whole bunch of virtual machines. So when the machine is blinking, that means that it's booting. Unfortunately, these things don't quite boot instantly yet. And then Bandit is assigning queries to those virtual machines. And the initial strategy that it picked is really bad, right? It seems to have provisioned like 8 virtual machines and then put all of the queries on one of them. Very dumb strategy, not smart at all. And we can see on the graph on the other side of the screen, the blue line, the top line, labeled rlearn currently, is showing the performance, the cost, the actual dollar cost that the Bandit algorithm is incurring. The orange line is showing a simultaneous run of this system, which you can't see, where we are picking the greedy optimal solution for each query. So we're saying, where could we place each query so that would be absolutely best, pretending we know the latency ahead of time, and making that decision. So clearly Bandit does not start out super well, but As it begins to learn, you can see that these queue lines get much shorter, the number of cluster machines sort of ends up stabilizing, and the queries end up being processing much faster. And if we let this go for long enough, eventually that blue line catches up with that orange line entirely, and the system converges to that sort of greedy optimal strategy. I'm not going to make you sit here and wait for it. I promise it does happen though. So one interesting thing to note is that, each one of these virtual machines, just like in our door example, is creating a gigantic experience set. So this virtual machine note, okay, when my CPU usage was at 25% and when my RAM was totally pegged, when I didn't have any more queries in the queue, when I had a query that was using 2 tables with this many estimated scans in a single join, when I accepted it, that had a cost of 12,000 units. Alternatively, when my RAM was significantly less pegged, and I was running a query with significantly fewer scans, when I chose to accept it, that only had a cost of 8. And so from these examples, the bandits can eventually learn, okay, when I see a query with few scans, I'm a good virtual machine to run that on. And it can learn to, from this experience, eventually to capture that information. And as you can see now, the lines are much, much closer to being converged. So someone asked a question earlier, are you running each one of these, Luba asked earlier, are you running each one of these in isolation? And so in that example, we indeed were, but one of the very nice things about Bandit is that it performs very well under concurrent query workloads. So we ran an experiment where we just ran one query at a time, just like the demonstration you just saw. And those are represented by those highest lines. So you can see that Bandit's curve initially starts out really terribly. It's spending a whole lot of money on average per query, and eventually converges to that dashed line, which is the greedy optimal. If we increase it to running one query per virtual CPU, so instead of running one query at a time, if we have an Amazon node with 2 virtual CPUs, now we run 2 queries at a time, the performance gets a little spikier. That's the second highest pair of lines. But again, Bandit converges to that nice clairvoyant greedy solution. If we increase things, if we oversubscribe our machines and we run 2 queries per virtual CPU core, we get a lot more variance. That's the bottom 2 lines, a lot of spikes, a lot of bouncing. But again, Bandit does kind of seem to, it doesn't quite get as close, but it seems to sort of approximate that greedy line. So this is a great result for real world cases where you obviously want to take advantage of query parallelism. The other nice thing that Bandit does that WiseDB can't really account for is new queries, right? So we've talked about, okay, a query workload and a query workload consisting of a certain thing, but it's very rare that an actual customer knows all their queries ahead of time and never wants to add a new one, right? Customers normally want to generate new reports, they want to start new businesses, they want to run new analyses, etc. So what we looked at in this experiment is Bandit's ability to adapt to new queries coming into the system. So in the top line, what we did is we took TPC-H, a system with about 22 query templates, and initially we introduced Bandit to 10 of them. Then after 2,000 queries were processed, we introduced the other 12 all at once. Bandit had never seen them before. And when we do that, we get a big old spike in cost. We introduce these new queries that Bandit's never seen. It doesn't know how to handle them at all, so we get this big old spike in cost. But very, very quickly, Bandit learns and adapts to these new queries and brings its performance back in line to around the average. The other experiment we ran is perhaps more realistic, where we introduced a few new queries at a time. So again, we started out with just the 10 TPC-H queries that are introduced all the time, but then at several different increments, here, 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 and here, we introduced one additional query. And when we do that, we saw a little spike and then a very quick recovery. So what this demonstrates is that even if your workload shifts drastically, Bandit is still able to recover relatively quickly. And if your workload shifts slowly, which is the more realistic case, Bandit recover, it's kind of just a blip on the radar. Bandit learns to adapt to that very, very quickly. So these are promising results that could lead one to believe that Bandit could be very applicable to a real-world system. So those were both top-down systems. We didn't really talk about the database management internals. All we talked about was sort of orchestrating the top level of the cloud. For the second half of this talk, I want to talk about the bottom-up systems that we've developed. So now we're going to be getting into the nitty-gritty details of where are the actual bits on the disk, what are the actual query plans, and how are they performing. So the first system that we developed in this vein is called NashDB, and NashDB is an elastic storage system that is designed to help users design fragmentation schemes for cloud workloads. So data distribution in a distributed database is probably the most important decision that you're going to end up making for your database application in general. So we know that static data distribution methods don't work, right? So normally with a distributed database, you have some kind of DBA who's sitting around, who's monitoring the workload, and who says, oh, hey, this really isn't working. We got to change things a little bit. We got to repartition something or re-replicate something. So the sort of two classical approaches to this problem are hash-based fragmentation schemes or value-based fragmentation schemes. So here I've shown an example of a value-based fragmentation scheme. If we have a table, T, and we know ahead of time that our queries are going to access one part of T or another, then I might say, okay, well, some of my queries are accessing the first half of T, so I'm going to put those into one fragment, and some of my queries are going to access this other half of T, so I'm going to put those into a different fragment. So here the first two are blue, representing the first half of the table, and the second two are orange, representing the second half of the table. So this is a pretty good partition and replication scheme depending on your workload. So if your query workload looks something like this, to sum up a column where the predicate is less than the midpoint or greater than the midpoint, this is a pretty good fragmentation scheme. You don't have to send any data to any other node. You can compute the query, possibly in parallel, on a single node using the data that's there. However, this sort of scheme doesn't work very well when your workload shifts a little bit. If your workload shifts a little bit, and suddenly instead of having half and half, now you have 1/3 and 2/3, now you have an imbalanced workload. Now, almost double as many queries are going to the orange fragments, the bottom fragments representing the second half of the table, than are going to the fragments on the top. Now, this is an easy enough situation to fix, right? If you have a DBA on staff who's sitting there, who's looking at stuff, they can go, oh, okay, well, we need to change our replication a little bit and fix this a bit. So this doesn't seem like it's a huge problem until you think about the cloud. And the cloud, unfortunately, really rains on this parade. When we say this model hits a wall when it comes to modern cloud computing, what we mean is that the cloud introduces a lot of complexities that these traditional approaches aren't able to deal with. The first additional complexity is that the number of nodes isn't fixed. In our previous example, our DBA reallocated one fragment and put it into a different place. That is fine for when you have a fixed number of nodes, but when you can add another node, that's another decision a DBA needs to make. Do I replace an old fragment, or do I add a new node and create another fragment there? Additionally, your workload doesn't shift or grow just once. It can do it periodically. If you're Netflix, this happens daily, right? Way more people start watching Netflix after work, and then way few people are watching it at 3 a.m. Maybe not that many, less, but approximately. It can also happen seasonally, right? Amazon sees a huge spike around Christmas and around other such holidays, right? So one option is you can have a DBA on staff, and if you're Amazon and you're doing it seasonally, that might be okay, to decide, okay, take this, replicate it, make it bigger. But you don't want to have a DBA sitting there daily, right? Netflix does not want to hire a person to spin down the servers at 5 a.m. in the morning, right? To just sit there and hit that button. We don't want to do that. Additionally, the cost of the cloud resources may change. So even if your DBAs are really good and willing to stay up super late, perhaps watching Netflix, they also have to keep in mind that the cost of these resources may have shifted underneath them. So it might have been the best decision to make last year when you had your spike in Christmas sales, might not be the best decision to make this year. And in fact, the prices of these cloud resources change monthly. So even month to month, those decisions might be different. Additionally, all your queries might not be equally valuable. If a user on Amazon is trying to change their password, you might be okay letting that take 500 milliseconds. But if they're making a purchase, you might want that to go really fast. Or if they're doing a search, you might want that to go really fast. So the underlying problem is that clouds are cheap, but DBAs are not. Hiring a human being to sit there and make these decisions for you is not a scalable strategy, even for the largest enterprises. So what most enterprises do now is they just pay for max capacity. They're just like, oh, well, here it is, we're going to do this. We're proposing a system, we've proposed, published, shipped out the door, a system called NashDB, which is a data distribution framework for cloud databases. So we make a couple assumptions about the workload. We assume it's a read-only workload or a very, very heavily skewed read workload, and an analytic workload, OLAP. So not inserts, not purchases, big analytic report-style queries. NashDB manages the data distribution using an economic model of the data. So we assume that when a user submits a query, that query has a particular budget that represents the priority of the query or the value of the query to the user. Those queries then pay nodes for access to tuples. And because a query pays nodes for access to tuples, we can think of each tuple as having a particular value. So if a tuple over the course of an hour is accessed 100 times by queries that each pay a cent, we can say that that tuple has an expected value of around $1. So I'm not going to talk about the details of how we track the value of each tuple in the database. Those details are in the dissertation. We have some nice new efficient data structures that handle it very well, but I do want to give you the intuition of what it looks like. So for a particular table, with, in this case, a very small table with only 35 tuples, we can track for each one of these tuples the approximate value of that tuple. So for example, tuple 5 here is not worth very much. It has a very low value, but tuple 20 has a much higher value. And so what we'll notice is that we get a lot of plateaus in this graph. And the reason we get these plateaus is because we're running analytic queries that are reading large chunks of data. So if we have one type of query that reads everything, that's going to give a tiny little bit of value to each tuple. If we have some queries that look at a particular range of rows, like say the last week of sales, then those are going to give a much larger chunk of their potential budget to fewer queries. And as a result, we get sort of a plateauing behavior where some of our queries are accessed a lot and some of our queries aren't accessed much. So what NashDB does is the first thing it does is it tries to group together tuples with similar values. And what we note is that this problem is isomorphic to inducting a decision tree on a data set with a single variable. And if that doesn't mean anything to you, that's okay. What it basically means is first, we make a greedy split of the data. We figure out, okay, where could I split this data such that I would get the lowest variance on each side of the node. So in this example, if I were to split it here, then I would get this red line as the average for these tuples and this red line for the average value of those tuples. Then, depending on the number of fragments I want to create, let's assume in this case I want to create 3 fragments, I can figure out which one of these sides I want to split again. So using your off-the-shelf decision tree induction algorithm, you can come up with a greedy approximation of the best way to fragment this data. There's actually a polynomial time, although it's quadratic, to find the optimal one as well. And that's all discussed in the dissertation. So once NashDB splits up these data into similar sized fragments such that the average value of a tuple within a fragment is similar, we can compute the value of the entire fragment. So for this fragment right here, because all the tuples have relatively high value, that's a very valuable fragment. These tuples, on the other hand, not so valuable. Their average fragment value is a little low. So what NashDB does is it says, okay, if it costs me $1 to store this fragment, and this fragment is worth $3, I should store it 3 times. If this fragment is $1.50, but it costs me 75 cents to store it, then I can only store that fragment twice. So we look at the value of the fragment and how much it costs to store the fragment, and we figure, okay, if the user wants to get their best performance while staying within their budget, we'll create the maximum number of replicas that doesn't go over budget. So again, seeing is believing. So here we have a tuple value graph from an analytic dashboarding query from a large corporation that was donated on the conditions of anonymity, etc. And so what we can initially see is that NashDB this is the tuple value graph, and so we have a couple of big spikes. And what these 2 spikes represent, the forward spike on the right represents them updating some recent statistics, so like stuff about the last week, and the bigger spike at the end represents scans over the data that are computing much larger aggregate long-term results. And so initially, WiseDB has said, okay, well, there's this big spike, this green fragment, the second fragment, is extremely valuable. So it's realized, okay, well, I should replicate that fragment 3 times. This yellow fragment, on the other hand, basically no one's reading this at all, so I should replicate it the minimum number of times, which in this case is 1. Now, as the workload progresses, eventually this stops being the case. Eventually, my green fragment, which I've replicated a lot, is no longer getting a lot of traffic, and now my red fragment, the fragment to the next to the green fragment, is getting much more traffic. So when this happens, NashDB recognizes this. It realized that the system is no longer in an equilibrium. It no longer makes sense to have this arrangement of fragments from an economic sense, and NashDB will refragment the system. It will redraw the fragment boundaries and say, okay, now we need this data in one fragment and this data in another fragment, and then re-replicate them across the database. So now again, the green fragment is quite popular, and it's replicated several times. We can run this on a live system, and we can see how NashDB continually adapts and changes both the size of the cluster and the number of replicas as the database workload changes. So that's a neat example because it has a lot of moving parts. We can also compare the fragmentation scheme that NashDB uses with a more traditional, naive, value-based approach. So if we were to do this exact same thing using a naive value-based approach, what we would see is that we're not adjusting our fragmentation based on where the data is being read. We've just made 2 duplicates of every single fragment, and as a result, some of the fragments are really underutilized, some of the fragments are really overutilized, and by the time we get to the end of the simulation, we've actually paid a much higher cost. So if we use this naive-based partitioning, we end up paying about 1,200 cost units. I think these are cents, sorry, so about $12, versus with NashDB, we pay about $8.60. Additionally, we also get better query performance out of NashDB. NashDB will execute queries faster because more of the highly accessed data is available. So NashDB runs about 60 queries per second, whereas the naive method runs more like 40 queries per second. So to give sort of a more intuitive understanding of what's going on here, here's a much simpler workload. This is not a real workload. This is a totally generic workload that's running live right now on Amazon because I just started it. So in our very simple workload, we have 7 different types of queries, and they each have a certain volume and a certain budget that they can go and execute themselves with. So here's the tuple value graph, and here's the current virtual machine configuration that NashDB has decided to use. And here is the average query latency of each one of these types. So I can see that query 7 is right now taking quite a long time. So if I want to automatically adapt my fragmentation scheme to make query 7 go faster, I can give query 7 more budget, which causes my fragmentation scheme to change and drastically reduces the latency of my query. So notice that NashDB can automatically adapt the entire cluster configuration based on that priority. If that's not so much of a priority, but query 5 is a large priority, then I can increase the budget of query 5, and I can see similarly the data be reconstructed for that purpose as well. NashDB also handles elasticity. So for example, if we have very few queries, and they're not very valuable, then instead of before where we had almost 9 virtual machines, NashDB will only create 3. And this is because NashDB is directly balancing the value of the workload to the user with the cost that the user has to pay for the cloud. And of course, if in this scenario, that really doesn't look great, sorry. In this scenario, your query latencies are going to be really bad. But if I increase their budgets and I tell NashDB, okay, I care about the performance of all these and I'm willing to pay for it, then your query performances come right back down. So analyzing a system like this is a little difficult because, and comparing it to other approaches is also not the easiest thing in the world. And so this sort of standard technique is to use something called a Pareto plot. So we compared NashDB against 2 other adaptive fragmentation schemes, one called SWORD, which is based on hypergraph partitioning. Essentially, it tries to make it so that queries never have to go across nodes to access data. And then another system called eStore, which is a thresholding-based approach, which essentially takes all of the, divides the database into 2 categories, hot tuples and cold tuples, takes the hot tuples, replicates them a lot, takes the cold tuples and tries to replicate them minimally. And so we analyzed a number of different configurations of all of these systems and created this Pareto plot shown on the screen. So on the x-axis, you can see the average latency that a particular configuration produces, and on the y-axis, you can see the cost that that latency incurs. So where you'd want to be is in this bottom left corner here. You'd want to have the lowest latency possible and the lowest cost possible. Unfortunately, we haven't figured out how to achieve that yet. But what you can see is this very nice curve right here. So all of the nodes that are closer to the bottom left than any other node is called the Pareto front. And as you can see here, NashDB dominates the Pareto front at every point. You would never want to use one of the other systems because for every other point, NashDB can either achieve a lower cost or a lower latency at the same of the other thing. So we say that NashDB is Pareto optimal because no matter what cost or latency you're targeting, NashDB is going to give you the best trade-off.
Is there a simple way to see why NashDB is such a fine line without spread where the others have so much of spread in them for a
Yes,
latency?
that is a great question. The reason is because both the hypergraph partitioning and the thresholding-based approach weren't designed for the cloud. They were designed for this traditional data center environment, so they don't actually have a notion of the cost of the resources being used. They assume that, okay, you've got a static cluster, it's this big, what should I do with it? And so as a result, they don't often make sane decisions, right? Like for the thresholding approach, it seems like the curve seems to be shaped the wrong way, right? Like this is the kind of curve that you'd expect, but the thresholding approach seems to kind of arc the other way. And that's because it's really inefficient to generate these sort of middle latency, middle cost scenarios because that's not really what they were targeting. they were targeting either the scenario where you want the fastest possible latency or you want this little possible cost. And because of that, they kind of get the wrong shape in the middle.
How much does it cost the Nash DB to compute in order to track the change, for example, when you partition? And how does it, I mean, I understand that those other guys cannot adapt, but how much it costs the Nash DB?
That is a great question, and to answer it, I'm going to cheat a little bit and open a different PDF.
Would you repeat that question, please?
Sure. So the question is, there's two questions. The first is, what is the overhead of the NashDB system? How much does it cost to do this automatic fragmentation? And what are the overheads involved, and how do we do it effectively?
The refragmentation in particular, right? Because
Sorry.
you're saying you can refragment. when you-
Right. So the way that we do the refragmentation is shown in this graph here. So imagine that the left side here represents the old fragmentation scheme that you're trying to get rid of, and the right side represents the new fragmentation scheme that you want to get. So essentially what we do is we try to find a minimal matching between the two, which there's a nice fancy algorithm that does it in polynomial time, so that we have to transfer the smallest amount of data between machines on the old fragment and data on the new fragment. So when we find this minimal matching, that gives us this nice property that we find a transition strategy that is minimal. It requires transferring as little data as possible. So that only answers half your question. So the first half of the answer is, well, what's the overhead? Well, it's minimal. So yeah, what's the actual overhead? So we ran an experiment on this. Might take me a second to find it. That's not it. So nice Pareto plots. You can see the schedulers, monetary cost. Where's the transfer cost? Is it down in the appendix? Ugh. There we go. Okay, so this plot is showing for each one of these systems, they're able to generate a fragmentation. So what we did to measure the different trade-offs between them was we took the system at state A, we ran the algorithms on them, we took the system at state B, we ran the algorithms on it, and then we've computed the minimum possible overhead between the two. And what we found was that indeed NashDB, the purple bar on the far left, does transfer more data than the other two approaches, but I really want to highlight the unit here, which is kilobits. So when you are, it's very, very, very low. The other systems indeed are lower because they changed the fragmentation scheme less. But for a 2 terabyte database between fragmentation schemes, we're transferring less than 200 megs. So essentially nothing.
So, but my question was not how much it costs you to refragment, which is I think what you're answering, but how much it costs to track when. In other words, how much is the how much you pay, how much NashDB pays for the adaptivity, because that's the cost of doing business, so to speak.
Right. So that is sort of encoded in those Pareto plots. We compare the cost of the overhead of NashDB with the overhead of a hypergraph or a thresholding system. I think maybe the experiment you're asking for is what is the overhead compared to not doing anything adaptive at all?
Right. I have to pay, and I pay the same money.
Right, exactly. So we have one example of that here where we show that if you don't do an adaptive case, if you just keep your fragmentation as low as possible the whole time, you end up paying a high cost and you get this particular query performance rate. So I don't have an exact quantification for you of the overhead, but what I can give you is evidence that the overhead pays for itself. Because here when we're doing the dynamic fragmentation, we're achieving a lower cost in a 50% increase in query throughput.
But then doing the optimal fragmentation doesn't pay for itself beyond the greedy heuristic?
No, it's not too bad. It's a quadratic algorithm, so it would depend on the size of your data. But in our experiments, we found that it's not too big a difference. Cool, okay.
Ryan, how often does NashDB reassess? Is it on every new set of queries that comes in? Or?
Great question. So in the original paper, we sort of punted, and we said the user picks a time interval, like 20 minutes, and it redoes it every 20 minutes. What we found was a much better approach later is that we can wait for the system to fall out of equilibrium. So if you think about every virtual machine as a firm that's trying to make a profit, and every query as a potential customer, the system is out of equilibrium when a firm would decide to close, or a new firm would decide to open because it would be profitable for them to do so. So what we found later and what we show in this demonstration is that we can wait for the system to fall out of equilibrium, and once it's fallen out of equilibrium, that's a good time to do a correction.
That's a quick question on this
Yes.
query plot. Is there any way to calculate the optimal, the limit, to know how close to the optimum NashDB does?
Yes, so we do. So this is on a real data set that's terabytes large. That's not feasible. We did it for some much smaller data sets where we could analytically compute the best possible solution. And we found in those cases that NashDB was about 20% off the optimal, and that the other systems were between 50 and 80% off the optimal. Okay. So the last system that we're going to talk about is QPPNet. So latency prediction is a very important component of a lot of different cloud systems. When you get a query that comes in, you want to know, is this query going to take a minute or is it going to take an hour? And if based on those two things, you might want to make a very different decision. So the query performance prediction problem, it's a classic problem in database systems. It has a ton of different applications, like capacity planning. If you're about to run a lot of really long-running queries, then you're going to want to get a bigger cluster. Admission control, if a user normally submits queries that only take 5 minutes and then they submit a query that takes an hour, maybe you want to say, hey user, are you sure? Did you write the right query? Do you really want to do this cross-join? And for scheduling, right? Like if we want to put the shortest job first, then we have to know what is the shortest job. It's also an extremely difficult task on its own, even with just static queries running in a static environment, but it's additionally complicated by the introduction of concurrency and cloud environments. So the current approaches can be divided into about 3 categories. The first is plan level QPP. In these, humans sit down and they look at a whole bunch of different query plans and they come up with features like how many joins are there? What tables is it scanning? Does it read the fact table? And they make a big old vector of these hand-engineered features and then they train a machine learning model to try to predict on it. There's also operator level QPP. In operator level QPP, human beings try to engineer a model for each individual query operator, like a scan or a join, and then they try to sum all of those up for a query plan to get a prediction for the entire thing. The main problem with operator level QPP is that it's agnostic to the structure of the entire query plan. When you're trying to decide how long a join is going to take, you're not taking into account how long the things underneath it are going to take. There are also hybrid approaches where a human being basically sits down and engineers both a model of operators and a model of plans, and then puts all that stuff into a machine learning algorithm and kind of hopes for the best. What all of these approaches lack, the problem with all of these approaches, we argue, is that they require this level of human hand engineering. So on one workload, it may be very relevant for you to engineer a feature like, does this touch a fact table, or does this use this particular predicate? But those features in general aren't really going to apply to other workloads. The other problem with these approaches is that they tend to be very ad hoc. The models that they create don't really have anything to do with what's actually happening inside of the system. When you take a query plan and you turn the entire thing into a vector, you lose a ton of structural information. You lose a ton of, you don't know if it's a left deep tree, you don't know if it's bushy, you don't know how much parallelism could affect it, and you lose a lot of that information. So the idea behind QPPNet is that we're going to learn the relationship between operator features and the plan structure. We're going to take a supervised learning approach, which means we're going to run a whole bunch of queries, get their latencies, then we're going to train something to do it. Because this is a computer science PhD dissertation defense in 2019, it has to use a neural network. That's just the law. And so I promise this will be the only slide that has math, but these are important boxes to check. You can think of a neural network as a series of activated affine transformations. And an activated affine transformation looks something like this. It takes in a particular vector, it runs it through some kind of differentiable activation function, like a ReLU or a sigmoid or a hyperbolic tangent, and then it applies that inside of a affine transformation, which is a linear transformation, wi times the vector x, plus some kind of bias b. You can think of a neural network then as the composition of many of these affine transformations put together. So you apply L1 first, then L2, then L3. And if we expand that out, we can see that the entire neural network's definition is still still represents a series of activated affine transformations. What's important about this equation is to note that n is differentiable. Because S is differentiable and because an affine transformation is differentiable, we can use the chain rule to come up with the derivative of n itself. Additionally, we can define something that we call a loss function. We can say that the loss function of this network over a particular data set is the difference squared between what the network predicts and what it should have predicted. So because the loss function is differentiable and because the neural network is differentiable, because each affine transformation is differentiable, we can compute the derivative of each one of the weights, each one of the values in our W vectors and our B vectors with respect to this loss function. And because we can compute that derivative, we can use standard gradient techniques to train these things. So as long as whatever you have represents a differentiable problem, you can look at the gradient of each particular weight, you can flip it around, and then you can say, okay, I want to make my loss lower, so I'm going to go in the other direction by some kind of small learning rate lambda. Okay. So with that being said, the way that QPPNet works is by learning the relationship between operator features and plan structure. So what we're going to do is we're going to design a very small neural network called a neural unit that's going to attempt to model the behavior of each individual operator. So for example, for a scan, I'm going to go into my query optimizer and I'm going to pull out a kitchen sink of information. All this information I could possibly have about a scan. What's the type of the scan, what's the optimizer cost, etc. All things that would apply to any workload. Then I'm going to run those pieces of information through some hidden layers and through an output layer. And that output layer is a little different than your normal neural network output layer. What this output layer does is it has a latency output. It tries to predict the latency of the plan. But it also has two things, or a number of things that we call a data output. And this data output is responsible for representing information about the scan operator that might be useful for the parents of the scan operator to make their prediction. So to put that in context, in addition to having a neural unit for the scan, we're also going to have a neural unit for the join. And so for the join in this query plan, which is just a join of two scans, we again take in all the information we can get from the optimizer, the join type, the predicted cost, what the hash function we're using is, if there's a spill predicted, that sort of thing. And again, run it through the same series of layers to get another data and a latency output. However, unlike a normal operator level model, we can then combine these neural units together. So because I have two scans here in a single join, I can take two instances of the scan neural unit and connect their outputs into my join unit. So because a join always has two children, the join will always take input from two different operators. We'll define every operator as having the same number of data outputs and the same number and a single latency output, which means that they can always be composed together in this way. So again, because the neural network structure is differentiable, by connecting these two scan units together into this join unit, I again get another differential structure, which means that this entire thing can be trained using your traditional stochastic gradient descent methods. So to make things a little more generic and high level, imagine that I have a query plan with two scans, a filter, and a join. I'm going to construct an isomorphic neural network. So I'm going to have my scan unit, my filter unit, and my join unit. Those are going to take in some information from the query plan, and they're also the non-leaf operators will take in the data vectors and the latency vectors of their children. So when we're training this thing, we initially create a whole bunch of queries. We execute those queries and observe their latencies. We build the isomorphic neural network for each one of them, and then we train it using gradient descent to teach each one of these neural units to do two things. First, each neural unit is trained directly to predict the correct latency for the operator. That's the most important part, well, arguably. We also train it to try to produce data outputs that are helpful for the parent. So because the gradient can be viewed as flowing from the top root node all the way down through the leaves, when the weights that are changing the outputs of this data output will be affected by whatever this unit needs to make its effective prediction. The weights of these data outputs will be affected by whatever this unit needs to make its effective prediction. And so we're learning automatically, with no hand engineering whatsoever, how our operators are interacting. And so if that sounds like it's pie in the sky bullshit, it's because it sounds like it is. So we're going to look at what this actually looks like in a real query plan. So what we're going to do is we're going to construct a query tree for a very simple query plan like this one. So this is a left deep tree with a single filter. And we're going to visualize the data outputs. So here we're going to use two data outputs. And the way that we're going to visualize the data outputs is like this. So if one of the data outputs is -1 and the other one is 1, then we're going to represent that as a big arrow pointing to the top left. If there's a lower magnitude vector, like -0.2, we're going to represent that as a skinnier vector pointing in the same direction. So this is just how we're going to visualize it. No fancy tricks here. So on the right side here, we have our prediction graph. So this is showing as this predicate changes, as the predicate on A becomes less and less selective, the latency of the query increases. This black line shows the true latency of the query. This blue line shows the prediction that the neural network is making. So in this case, we're seeing that it's pretty good. So as we increase the selectivity of the predicate, we can see that the neural network's prediction at the root node is increasing, which is all good and well. And if we run this, if we increase this predicate all the way up, we can see that those data vectors are changing as well. So we're not, I'm definitely not claiming to know how neural networks work or to be able to look inside of these things and determine the actual human intuition behind what they're doing. But in this particular case, we can analyze these data vectors and try to kind of figure out what they might be learning. So it happens to be that both of these two join operators are implemented inside of the database as a hash join. So the left side of each one of these join operators is the build relation. It's the relation that it's going to build a huge hash table out of. And the right side is the probe relation, which is the relation it's going to step through and it's going to look for a match in the build relation. So the reason that this query latency looks like this, looks kind of exponential here, is because these hash joins spill. As the number of tuples coming in from A increases, eventually they get so high that they don't fit in memory anymore, that this hash join build requirement has to spill to disk. And spilling to disk is very, very slow. And so we see the point where the first hash join spills, this hash join, the lower one, is right here, and the point where the second hash join spills is right here. So after the first hash join spills, we get a little bump, and when the second hash join spills, all hope is lost, and things skyrocket drastically. So I want you to watch what happens to this data output of this join as we approach the spill point. So it's not really moving, not really moving, not really moving. Oh, it's getting a little thicker. Starting to move. So interestingly, the data vector undergoes this change in magnitude and rotation, drastic change in magnitude and rotation, right as the hash join spills. Now, this doesn't mean that the neural network learned how to detect a hash join spill. It might have learned something that correlates very strongly with a hash join spill. But it's still, kind of an interesting result. And what's really interesting is that this top join, now watch its data output, slowly but surely reaches, once we get to its point where it spills, it also rotates in a very similar way. So the data outputs, we don't know exactly what they're learning, but in this case, they're definitely learning something that looks a whole lot like, when is this hash join going to spill? And note, we didn't give it any information about that. We didn't tell it what the hash join was. We didn't tell it what the memory requirements of a hash join were. None of that at all. It learned all that from the data itself. And so when people say that deep neural networks are good at feature engineering, this is what they mean. The neural network learned that without us giving it any information other than the kitchen sink from the optimizer. So if we now have a couple graphs, I know we're running out of time. I promise we're almost done. So we did a big old analytic study of this, and you can find all the details in the dissertation. But what we find consistently is that QPPNet will outperform handcrafted solutions, whether they be operator level, plan level, or hybrid, on synthetic benchmarks as well as on real data. Here I'm showing TPC-DS and TPCH, which are two synthetic benchmarks. One thing that has been suggested to us is that this tree structure thing isn't really necessary. Why don't you just use a vanilla deep neural network to try to see how that works? So we tested that as well, and that performs extremely poorly. So it turns out that the tree structure of the query plan really does contain a lot of information that is relevant to how the query works, which is entirely unsurprising to database people and maybe a little bit surprising to machine learning people. So the answer here is that this is not a case where you can just throw machine learning at the problem and hope for the best. You actually do have to think about the architecture of your network, and you have to make it map the problem that you're solving. So this is often called inductive bias in the machine learning world. If you just have a deep neural network that's regular, that could be any function. You haven't really told the network or restricted the network in any way. So it's going to learn something that works pretty well in your training data, because it always does, but it's not going to generalize. If you induce some bias into the neural network, if you tell it, hey, this thing has a tree structure and this latency output determines this latency output, then you're going to learn a neural network that generalizes a lot better. So one of the really nice things about this is that we can easily adapt it to handle concurrent queries. We can take two of these trees and we can connect them at the top, and then we can train it to predict the concurrent latency as well. So we compared this against the buffer access latency, or BAL, which is the current state-of-the-art approach in concurrent query prediction, and we note that for at least for multiprocessing levels 2 and 3, running 2 queries at a time, running 3 queries at a time, we get a nice little boost. So the first bar on the left here is representing what that hand-tuned heuristic approach does, and the second bar is representing our error. And you can see that the standard error on the heuristics is something like 40 and 50, and for us is approximately 10 or 20 minutes lower. So that's quite nice. We get a much better prediction in these concurrent cases as well. Now, this is a deep neural network, which means it's not the cheapest thing in the world, right? These handcrafted heuristics might just build a vector with 5 or 6 things in them and then do something very simple. So we analyzed how long does it actually take to do a prediction, and while we are not Pareto optimal, we are Pareto efficient. So this graph is showing the orange boxes represent QPPNet, the trade-off between the error that you incur and the inference time that you take. So again, where you want to be is down in this lower left, but all the solutions are more or less close to that. So the TAM approach, which is a very simple linear regression model, has very, very low inference time, but pretty high error. Our approach has admittedly much higher inference time, almost up to 100 milliseconds, but drastically lower error. So depending on your application, this might be acceptable or not acceptable. For example, if you're doing query admission, 100 milliseconds is nothing, right? If you're talking about a query that's going to run for hours, running a 100 millisecond check on it, no problem at all. However, if you wanted to use this for query optimization, like if you wanted to use this as part of your optimizer in your plan enumerating process, maybe 100 milliseconds isn't going to cut it. So yes?
So times are measured on CPU for both deep neural networks and the other models?
Yes. So that's a good point. Deep neural networks, their structure, the fact that you have so many matrix multiplications leads them to naturally perform much better on specific hardware for them, like GPUs. So it's possible that if we used a GPU, this inference time would go down. It probably wouldn't affect the inference latency, because then you'd have to copy data to the GPU, do the computation, and copy it back. But if you needed to cost like a whole bunch of query plans at once, the throughput might be higher.
But your trees are all different, right? So you can't.
Yeah, so the trees are all different, so you can't really even get that. You can get parallelism in the matrix multiply, but
right.
Yeah, not a lot of batching. Okay, so it's worth noting that right now the handcrafted heuristics are working. We seem to be getting okay performance out of them, but we should read the writing on the wall a little bit. And if you look at the best possible performance that we can get out of handcrafted heuristics over the years, it looks approximately linear. And if you look at the best possible performance that we can get out of cloud systems, it looks like it has a completely different shape. So the complexity of cloud systems is increasing much, much, much faster than we can design handcrafted algorithms to work for them. And so right now it's working pretty well. The handcrafted heuristics, they seem to be doing fine. But very, very, very soon we're going to reach this precipice where the complexity of the cloud system becomes way, 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 way bigger than a handcrafted heuristic can possibly optimize. And the primary argument of this thesis is that we should use machine learning to fill in this gap. The way that we can combine our handcrafted heuristics with machine learning systems will hopefully allow us to achieve much better performance, even as the complexity of the cloud goes up more. So in summary, we talked about a whole bunch of different systems. I know I'm a little over time, so I'm not going to name them all again. Yeah, that's it. Thank you. So happy to take questions. Yes.
Well, you can go back one graph, and why do the handcrafted ones beat the automated systems at the low time level?
So initially, when cloud systems started, they were bad. They were bad, to be frank. You could provision a virtual machine, but it might take a couple hours for that machine to come online. They would crash all the time, and basically you could get one machine, and that machine would run for on average 8 hours, and then it would crash. So there's not a whole lot you can do with that, right? There's some things you can definitely do with that, right? It gives you some elasticity. But over time, the options that the cloud provides are becoming bigger and bigger and bigger, and they're becoming bigger very quickly. So we should read the writing on the wall, and we should realize that we're not going to be able to hand-tune a system for every cloud customer. It won't work.
So, being not from computer science, I forget the word you showed, but where you showed that the data output was that arrows were fluctuating when something was happening when is that very thing which happens always in neural networks, or is it a particular case? Like, is there certain points when they suddenly learn that now I got to change my learning? Is it very sharply defined?
Yeah.
Or is it a generic thing, or is it something, a case about your application here?
So most neural networks use activation functions that look a little bit like a sequence. You know, they start out flat, and then there's sort of a spike, and then they level off again at the top. And the reason for this is the biology of the brain, actually. Like, we know that neurotransmitters in the brain have this sort of behavior where they get charged, and they get charged, and they get charged, and then suddenly there's some threshold, and suddenly they turn on and output themselves. And so we pick these activation functions to sort of model that in the brain. So this idea that something is going to build up and build up and build up and then suddenly cause an activation, suddenly cause a neuron to turn on, so to speak, is common across most neural networks. The fact that it lines up so well with a semantic thing that we can notice, that is not guaranteed. Right? So it worked in this case probably because we restricted the data output to just 2 values that we were able to see this. But in general, that's an open question in machine learning to try to figure out what exactly is each one of these layers learning.
And one quick thing, how did you decide how many layers you're going to put? Like, is it like some standard thing to do, or?
So we did something very simple, which I think is very common. We just did a grid search. So we said, okay, we have these 4 parameters that we can vary between 0 and 1024. So we're going to get a whole bunch of computers in the cloud, and we're going to try them all. And so we evaluated every point in this gigantic grid space, and we got all the results back, and we said, aha, that's the best one. And it's not very intuitive.
So it's
why?
a brute force search, okay.
Yeah. As far as I know, figuring out the best network architecture ahead of time without doing this is also a problem machine learning people are still working on.
In the WiseDB system, the algorithm you use, you cannot do large NP problems. So instead, you did a lot of small NP problems.
Right.
Now, how do you know that the solution you got there is going to be applicable to the large NP problem?
Great answer. Great question. Sorry.
I'm waiting for the great answer.
Yeah. So the argument that we make as to why that's going to be the case has to do with the interaction between the deadline and the latency bins. So for example, if your templates were all 1 second, 2 seconds, 3 seconds, and your deadline was something like 6 hours, that means your problem size in order to fill up one bin is going to have to be really, really, really big, right? You're going to need like a couple thousand queries in order to fill up one virtual machine to meet your deadline. But in this situation, where we have 3 minutes and we have 1 minute, you're only going to need 3 queries before you start seeing patterns, right? So yes, indeed, you cannot solve NP-hard problems, and there's no guarantee that the alignment of the small cases matches up with the optimal thing to do in the big cases. But in the general case where the deadlines are tight, where you aren't willing to wait 100 times longer than the query latency in order to get your result back, there's a much closer connection between what happens in the small cases and what happens in the big cases. So the assumption, which I didn't state, is that you're not willing to wait. If you have a 1 minute query, you're not willing to wait an hour for it. You want it kind of back faster.
Okay, thank you everyone. So me and Luba are staying, and Ryan, and the rest you can wait outside.
And Magda as well, who we hopefully didn't lose.
What
Did we
language
lose?
were the demos written in?
A variety. The WiseDB was written in Java. The NashDB one was written in Python, and this last QPP one was written in a combination of C and JavaScript.
Magda gave up.
Thanks, Nick. Oh yeah, watch out. All right, just a second.